The next question. Question 10. When a ship is sailing on a rough sea, the waves can set the ship into a simple harmonic motion. So the movement of the wave can cause the ship to have a simple harmonic motion. This can result a passenger become seasick. What is meant by the term simple harmonic motion? So how we define? So how we define the term simple harmonic motion? Simple harmonic motion means when the acceleration is directly proportional to displacement and the motion is always directed toward the mean position. Or you can also say in a simple harmonic motion, the resultant force is proportional to displacement from the equilibrium position and it is always directed towards the equilibrium position. Like direction of force and acceleration is. The next is at one position. In the previous question, look, the first part was the rubber feet maintain a contact between the speaker and the surface. Explain why a sound is loud when a speaker is on a hard wooden surface. So when it is on a hard wooden surface, the speaker causes a wooden surface to vibrate and wooden surface will have a large area as compared to the speaker. That's why the sound will be louder. And then the second part, they're asking why certain frequencies are louder, because when the frequency matches with the natural frequency of the wood, it will cause a maximum amplitude of vibration. That's why only certain frequencies are louder. The next is at one position. At one position on a ship, the passengers experience a vertical oscillation with an amplitude of 0.85 meter with a period of 6 seconds. We need a maximum acceleration. For a simple, look, what is the formula for a simple harmonic motion? For acceleration, if we need A, like if we need V is equals to A omega. If I need the maximum velocity, but if I need the maximum acceleration, so it is equals to A omega square. This is a formula which we can use for calculating a maximum acceleration of a simple harmonic motion. Which is A times omega square. How to work out omega? You have the time period. So omega is equals to 2 pi f. And frequency is reciprocal of the time period. So I can also say omega is equals to 2 pi divided by t. What is capital A is representing? Capital A is representing amplitude. And the formula like A is equals to minus, like small a is equals to minus the amplitude time. Why negative sign? Because that's the formula that the acceleration and displacement are proportional and the acceleration is always directed towards the mean position. So negative sign is only just to indicate a direction. So it will be minus, what is the amplitude? 0.85. What about omega? Omega is equals to 2 pi divided by t. So 2 into 3.14 divided by time period. It was 6. And then the whole square will be there. So when we simplify, this will give us the value for A. Yes, you can also do the same method. if you want to work out like acceleration and then the time, it will give, you will get the same result. So the final answer of acceleration 0.93 meters per second square. But as you are doing a question related to a simple harmonic motion, so usually the mark distribution, like writing a formula for omega, writing a formula for acceleration of a simple harmonic, that is having a mark. So negative 0.93 will be the acceleration. As you can see, passenger on a ship may suffer from seasickness as the ship rise and fall on the wave. The graph shows the limit of the passenger tolerance to the oscillatory motion. So acceleration divided by acceleration due to gravity, that's a ratio, because like if a ratio is like less than zero point 0.1, it is not noticeable. And if it is zero point 0.2, less than zero point 0.2, or around like between zero point 0.2 and zero point 0.3, it can be tolerable. And if it is from point like this region, if we have a value in this region, we won't notice that. Here we can tolerate, but any values above, it will be uncomfortable and intolerable. Negative sign only indicate the direction. If you don't write a negative, that's also fine. The magnitude is usually having a mark. So next is determine. The question is determine whether the passenger are likely to feel seasickness as a result of this ship motion, and you should use your answer for B1 and show that uh, how you use the graph. So how we can, because first the acceleration divided by acceleration due to gravity, that ratio means acceleration of a simple harmonic motion divided by acceleration due to gravity. So what is the answer here? Because this was 0.93. The last value which we calculated was the acceleration was 0.93. And what about this value? So this is 9.81. 0.93 divided by 9.81. What's the answer? 0.095. So we have 0.095. So where I will get 0.095 means I will get in the region of a not noticeable. And what was the period of the motion? It was 6 seconds. So where I will have these results, or it can be tolerable, because 0.095 somewhat here, and the duration was 6 seconds, like the time period was 6 seconds. So we will have a point here. So where it is lying that it is in a, it can be tolerate, or it is there in this region. Is it clear? Yes, we can tolerate this, so it won't cause us it won't be uncomfortable for the passenger with this acceleration. So from a graph, we can say it is tolerable. So there's a low chance of a seasickness. Now the graph shows how the vertical displacement x of a passenger vary with the time. Add to a graph to show how the acceleration of a passenger vary with the time. Now, when we work out the acceleration, because we know displacement and acceleration in a simple harmonic motion, acceleration is directly proportional to displacement, and a negative sign indicate it is always directed towards the center. If this is a displacement graph, what will the acceleration graph? Because this is representing a graph show vertical displacement of a passenger vary with the time. Like passenger is going up and then passenger is going down. So what about the acceleration? And I mentioned that acceleration and displacement time graph are like mirror images of each other. So this will be the acceleration. As the displacement is decreasing, acceleration will increase. And it will become positive. Then if a displacement is increasing, acceleration will decrease with the same period of increase and decrease. So this will be the shape of the acceleration time graph for this. Is it clear? Yeah, so it will be a reciprocal. The two graphs are always reciprocal of each other. Like what function it is giving, if you compare this function, so this is starting with the maximum value, so this is a cosine. So we will have a graph for acceleration, it will be minus cosine. And what is a minus cosine? So it will start with the negative axis and it will change. Yeah, this is related to sine, and because remember this graph is starting with the maximum value. So means this is a cosine graph. If a displacement is a cosine, what about the velocity? Derivative of cosine is minus sine. So velocity will be minus sine. If they ask us sketch a velocity time graph, so this will be the shape of the velocity time graph. So shape of a velocity time graph will be like this. And what about the acceleration time graph? If I take a derivative of cosine, it is minus sine, it will be negative cosine. So means the negative cosine graph with the same period. So from where it will start with a negative value, like negative maximum, then it will be positive maximum, then negative maximum, then positive maximum. But these should be same, like the positive and the negative maximum should be same. No, it won't be fully negative because acceleration, it cannot be fully negative in a simple harmonic, as when the object is moving towards the mean position, the acceleration is positive. When it is moving away from the mean position, then the acceleration is decreasing. When it is moving towards, the acceleration is also increasing. But what about the value? If it is moving towards the right hand side, if the values are positive, moving towards the left hand side, the value will be negative. That's why we should use both axes. As the object undergo a simple harmonic motion, so acceleration, magnitude of acceleration will change, as well as the sign, like example, when the acceleration is positive or negative, depending on which direction the object is. If an object is accelerated toward the left hand side, if we call positive acceleration, if it accelerated toward the right hand side, we'll call negative acceleration. And the other way around, we can also say, is it clear? The two graphs. The time period will be same. The time for the change in acceleration and the time for the change in displacement will be same. The period will be same, but they will have a opposite. Like if one is cosine, another one is negative cosine. If one is sine, other one is negative sine. A passenger on the ship stand on a weighing scale. When a sea is calm, the reading on the weighing scale is 75 kilogram. Draw free body force diagram of this passenger. So free body force diagram represent all the forces which are acting. And here, when the sea is calm, so it means it's not going upward, so it is calm. So the weight is acting downward and a normal contact force for a passenger will act upward. We can represent the normal contact force with letter R, or we can also say write with letter N. But it should be same length. Why it should be same length? Because as a sea is calm means like it's not causing it to move up or down. So as a result, the weight will be equal to normal contact force. The next is on a rough sea, the ship oscillate vertically with a large amplitude. Why the reading? Why the reading on the weighing scale is vary? So like first when it was calm, the weight was acting downward and the normal contact forces act or a normal contact force or R was acting upward. But now when the sea is rough, the reading is changing. What is the reading? Remember, reading on the balance or reading on the spring balance or reading on the weighing scale is actually the value of a normal contact force, R. If the value of the R is not changing, it means the reading on the balance will remain unchanged. So, like example, when the passenger is above the equilibrium position, this is the equilibrium position. Like this is showing a variation. What about the equilibrium position? These dots are representing the equilibrium position. So when the passenger is above the equilibrium position, like a passenger is standing on the weighing scale and he's above the equilibrium position. So what will happen? The weight is a constant which is acting downward. When he is above the equilibrium position means like he is forced to move up. And reference he is stationary. Like example, if I say weight of the passenger was 700 Newton, so the normal contact force is also 700 Newton. But here what will happen? The weight is 700 Newton and when he is at this position above. So there is some force because there must be some force to push something up. So means there is already a force of example 200 Newton. So how much will be the normal contact force in this case? So the normal contact force will be equals to 500 Newton. So as a result, what will happen? The value of the normal contact force will decrease because relatively he is stationary, but he is being pushed up by the waves as he is above the equilibrium position. So he's being pushed up. So there is an upward force as well. So what will happen to balance the downward force? If already 200 force is upward, so remaining 500 is there. So the normal contact force will be 500. If the value of the normal contact force decreases, it means the reading on the balance will also decrease. Is it clear? The first part, this part A, like why the reading will decrease when he is above the equilibrium position. And same way when he is below the equilibrium position, what will happen? Because to get below the initial position, there is also a downward force is there. Like let's say 700 Newton is a weight, and there is also a downward force to push, like move downward from the equilibrium position. So example, a 200 Newton downward is there. So how this will be balanced? So this will be balanced by a 900 Newton upward force. Because the object relatively remains stationary. It's only like moving away or like above the equilibrium position or below the equilibrium position. So when it is below the equilibrium position, greater downward force to balance that, more upward force or normal contact force increase. So the reading on the balance will increase. When object is above the equilibrium position, there is an upward force. So as a result, less normal contact force or smaller normal contact force. So the reading on the balance will decrease. Is it clear? Any doubts in this? So the next is the passenger is standing on a weighing scale. The maximum acceleration of the ship is 0.7 meters per second square. Calculate the maximum reading on the weighing scale. So when we'll have the maximum reading, when he is below the equilibrium position, that case we'll have a maximum reading. So if I sketch the position, like here I will have a maximum reading on the balance, and at this point I will have a minimum reading on the balance. So if I write the expression like weight is acting downward, normal contact force is acting upward. Which force should be greater to cause a greater downward acceleration? So it means weight minus R should be equals to resultant force. Like because it is going like moving towards like moving away from the equilibrium position. So it means the weight should be more than to have a greater like W minus R is equals to MA. And then when we simplify this, so it will be W minus R is equals to MA. What is mass times the acceleration? What about the weight? Weight is mass times the gravity. So I can also say mg. And the expression, the direction of x, because look, the idea is that whenever object move in a simple harmonic motion, the force resultant force is always directed toward the center. So it means if an object is put this position, so the resultant force should be directed toward the center. When object is at this position, the resultant force should be directed toward the center. So it means if I want a resultant force to be upward, so it means R should be greater than W. So R minus W is equals to resultant force. And if I need R, the reading, that is a resultant force plus W. Resultant force is MA and W is mg. So MA plus mg, when I simplify, I'll get the value for R. Is it clear? So the mass m I can take common, so it will be a plus g, where a is the acceleration of the system, which is 0.7, and g is a gravity 9.81. And m is a mass, which was 75 given in the beginning. So we got about 80.4 kilogram. So that's how we get the maximum reading. Same way, when it is above the equilibrium position, like if let's say they ask the minimum reading, they ask. So how you will solve if you need a minimum reading? When object move in like undergo a simple harmonic motion, resultant force is toward the center. So means the resultant force is downward. So if resultant force is downward, it means the weight should be greater than the normal contact force. So W minus R is equals to resultant force. And if I need R, W minus F. Weight is mass times the gravity and resultant force is Ma. So in that case, it will be mg minus Ma, and we'll get the reading. So remember, reading on the weighing scale is always refers to the normal contact force which we experience. Is it clear? Discussion? The next is a child of a mass 35 kilogram is standing on a trampoline. At equilibrium, the surface of the trampoline is displaced vertically by 22 centimeter from an unloaded position. So means it has moved 22 centimeter from the unloaded position. The first part show that the force of a constant show that the force constant of a trampoline is 1600 Newton per meter. So if we need this force constant because it's force divided by length, so it is actually like K, it will be F divided by X. So how much force is there? The force is because the weight is acting downward, weight is causing causing it to stretch. No, if a child of a mass 35 kilogram is standing on a trampoline, so the moment this is how the membrane of a trampoline will look like, the surface of a trampoline. But if someone is standing here, then what will happen? Then there will be a bulge and it will bend like this. When the child is standing, so when he stands, the surface of a trampoline will become curve. He's not jumping right now, he just stand on the trampoline. So it will be the force is mass times the gravity, because the weight of a child is causing it to displace. So weight is mass times the gravity, 35 times 9.8, and divided by how much it is, like 0.22 is there. So we'll get the force constant, which is, what is the value of a K? Okay, 1560 Newton per meter. 1561 Newton per meter. That's the value for the force constant. The next is the child bounce up and down, always staying in contact with the trampoline. Calculate the child frequency. So if we need the frequency, we have the formula that omega is equals to 2 pi f. So omega is equals to 2 pi f, and how we can work out the value for omega? Here, we need a frequency. So, but to work out the frequency, we need omega. So it means this formula, like here, the frequency, but we don't have anything related to a frequency. That's why we cannot use this formula directly. Then what else we can use? As you can see, the child is in contact with the trampoline. So the force from the child is actually causing it to vibrate, as it is oscillating up and down, moving up and down. So it means that the force from the child is causing it to vibrate. And what is the force in the centripetal, like simple harmonic motion? We have the formula F is equals to ma. And A is equals to, so we can say F is equals to m. A is the amplitude omega square. We did this formula in the last question. So it means the force which is applied is equals to ma omega square. And how much force is applied? So how we can work out how much force we applied here? We have the formula F is equals to K delta X, because whenever object stretches, according to the Hooke's law, that the force is directly proportional to extension, and we replace with the proportionality sign K. So F is equals to K delta X. So mean the force which is applied is causing a stretching, which can be given by a formula K delta X, and K we already calculated here. So I can write that the force which is causing a simple harmonic motion, which is ma omega square, is equals to K delta X. We have M, the mass of the child is there. We have A, the amplitude is there. We have K, which we calculated in this part. We have the delta X. Delta X is like the amplitude itself. So using this, we can work out, just we have to take a square root and we'll get the value for omega. And after getting the value of omega, then you can use omega is equals to 2 pi f. So A and this delta x, in this example, A and delta x will be same. Why it will be same? Because like if I say if it is stretches 2 centimeter, so and the amplitude and I release the object is vibrating from mean position 2 centimeter. So in that case, the amplitude will be same as the display, like the extension will be same as the amplitude. So this will cancel with this. So we will have omega square is equals to k over m. And I take a root both side. So omega is equals to under root k divided by m. So we'll get omega from here and then divided by 2 pi. So we'll know the frequency. Is it clear, this one? But we know the force. Why can't we use F is equals? Yes, we can use that. That's why I'm saying it won't make a difference. I just write a formula so that how you will reach this, that the omega is under root k divided by m. Like we normally, if it's something is there with a spring or a force constant, we use omega is equals to k divided